Welcome to this session of EMTL, which is a small topic, Ampere's force law. Now the reason I am telling this small because similar kind of law you have seen in unit 1. That was in electrostatics. This is in magnetostatics. Now what are the similarities? In unit 1 we have seen Coulomb's law, which deals with electric forces existing between electric charges. Whereas in second unit, we see Ampere's force law, which deals with magnetic forces existing between electric conductors. I just want to make out the clear difference. In unit 1, you have one force law. In this unit 2, you have another force law. Two force laws. Now, what is the difference? In unit 1, this force law refers to the electric force. In unit 2, this force law deals with magnetic force. Because unit 1 is electrostatics and unit 2 is magnetostatics. Now, electric force law is nothing but Coulomb's law, and this magnetic force law is nothing but Ampere's law, which is the discussion of this session. Now, if you observe carefully, in unit 1 I referred it as Coulomb's law, whereas unit 2 I am referring it as Ampere's force law. I am not just saying Ampere's law, I am saying Ampere's force law. In unit 1, I am not saying Coulomb's force law, I just say Coulomb's law. But unit 2, I can say Ampere's law, but I am not saying like that, I am saying Ampere's force law. What is the reason? It's very simple and straightforward. Because in unit 1, there is only one Coulomb's law, whereas in unit 2, you have two Ampere's laws. Number 1, Ampere's circuital law, which you have seen already in the earlier sessions, and the second two is Ampere's force law. So Ampere's law comes in two forms in unit 2. Number 1, Ampere's circuital law, and number 2, Ampere's force law in the same chapter. So I have to be very specific in mentioning. I cannot just say that Ampere's law. Which Ampere's law? Whether it is circuital law or force law. So I have to be explicitly mentioning it is Ampere's force law. That's the difference. Now, Coulombic law or Coulombic forces are nothing but electric forces. In Ampere's law, Ampere and forces are nothing but magnetic forces. Now, moving on to the actual discussion. Now, this is the expression for Ampere's force law. Force is a vector, but I did not keep any bar here. That we'll discuss now, subsequently in the same session. Now, for the moment, just understand we are focusing on the strength of the magnetic force, or technically speaking, magnitude of the magnetic force. So, what Ampere's force law deals with? Ampere's force law deals with the magnetic force existing between electric conductors. Now, I just want to make a distinction once again. That is, if we have two electric charges, namely Q1 and Q2, there exists an electric force between them, which simply means electric force exists between electric charges. Then where do you get magnetic force? A current carrying conductor is surrounded by magnetic field. That magnetic field can exert magnetic force. I repeat once again. If you have a conductor in which current is flowing, you just forget about the direction of current. Direction we will see subsequently. First you focus on the magnitude. You have a conductor in which or along which current is flowing, then you know a current carrying conductor is surrounded by magnetic field. So magnetic field will be surrounding this. Magnetic field, this produced magnetic field can produce magnetic force or can extend magnetic force. Why? You know what is the definition of electric field? The electric field is the amount of electric force exerted on a unit electric charge. That means in the definition of electric field itself, there is electric force. E bar equal to F bar by Q. The electric field can exert electric force on an unit electric charge. That electric force per unit electric charge is nothing but electric field. So in the definition of field itself, there is force. Fields can exert forces. Similar to electric field, magnetic field can also exert magnetic force on magnetic charges. Like electric field is exerting electric force on electric charge, magnetic field can also exert magnetic force on magnetic charges. Isn't it? So now, this is one option. There is another option. Magnetic field can exert magnetic force on another electric conductor, because there is also magnetic field surrounding that another conductor. These two magnetic fields, they may aid each other, they may oppose each other. If they aid each other, you get one scenario. Like in electric force, you have attraction, repulsion. Like that, you have magnetic forces being attractive, being repulsive. Now, what are the factors that will decide the magnetic force? Let us make comparative study once again. What is the expression for Coulomb's law, which means electric force? Because we are comparing one-on-one, electric force and magnetic force. F equal to Q1 Q2 by 4 pi epsilon r square. Electric force is proportional to product of electric charges Q1 Q2. Magnetic force is proportional to product of electric currents I1 I2. Here Q1 Q2, here I1 I2. What are I1 I2? I1 is the current flowing in the first conductor, I2 is the current flowing in the second conductor. Now, the amount of electric force is decided by product of electric charges. The amount of magnetic force is decided by the product of electric currents. Now, the thing which is not there here, which is there here is L. Because Q1 and Q2 are charges, point charges. But I1 and I2 are the currents flowing in the conductors. Then immediate question is, if the current is flowing in the conductors, then what are the lengths of the conductors? L stands for length of the conductor. That is there, which are different in comparison with these two forces. Next, you find mu here. You find mu here, whereas in electric force, you have Q1, Q2 by 4 pi epsilon r square. You find mu here, you find epsilon here. What are they? They are the properties of the medium in which you are determining this. This means force. You say the amount of force existing between Q1 and Q2, but where are Q1 and Q2? They are in the medium. What is the property of medium? Like that, epsilon and mu are the properties of the medium in which you are placing these charges or placing these conductors and calculating the forces, where you are doing this, all these things in medium, in some medium. For simplicity of analysis, if you take the medium to be free space, then mu will become mu naught, epsilon will become epsilon naught. However, in practice, the medium need not be free space always. It may be some other medium. So that's why I'm not taking mu naught and epsilon naught. If you want, you can take them for simplicity of analysis. So mu and here epsilon. So what is the similarity? The similarity in these two force, Coulomb's force law, Ampere's force law, one similarity is that in the determination of force, means in the force determination, whether it is electric force or magnetic force, the property of medium is considered. Because this is electric force, we have taken electric permittivity. Because this is magnetic force, we have taken magnetic permeability. When you are calculating magnetic force, you take the magnetic property of medium, which is magnetic permeability, mu. When you are calculating electric force, you take the electric property of the medium, which is electric permeability. Justified. Now, we can make one more reasoning out. Here, the property of medium is in the numerator. Here, the same property of the medium is in the denominator. What does it mean? Properties of mediums are there. They are counted in both the expressions for force calculation. But why here in the denominator and why there in the numerator? The reason is, what is epsilon? It's a property of medium, no doubt. But epsilon is the electric permittivity of the medium. Permittivity means the ability of the medium to permit, to absorb, to grasp, to take. That is called permittivity, to permit. So, if a medium has higher permittivity, the influence of the electric charges are more permitted, more grasped. Hence, the two charges can exert less force on each other, because medium is trying to grasp the influence or the impact of the electric charges on each other. So, charges are left over with lesser influence on each other, means lesser force, simply speaking. Whereas here mu is magnetic permeability of the medium. Permeability means permeating nature, to pass through, to allow through it. So, if the permeability is more, the influence of the magnetic fields can easily pass through, permeate in the medium, hence exerting more magnetic force. That's why mu is in the numerator here, epsilon is in the denominator here. Both are forces, both are medium properties, epsilon mu. One is there in the numerator, other is there in the denominator. Next, what else you can find out? Next, you have 4 pi r square. Why 4 pi r square? Because you have an electric charge here, there is one more electric charge here, there is a force existing between two electric charges along the line journey. If you take this charge and keep here, does this electric charge exert the same force? Absolutely same force, provided the distance is same. If the distance is r, it doesn't change, you have same force. If you place the same electric charge here, you also, with the same distance, you also get the same force. So, all around this electric charge, wherever you move this, provided uniform distance, you get the same electric force measured anywhere on the sphere. But what is the surface area of sphere? 4 pi r square. Because this is a sphere, it has surface, the surface area of sphere is 4 pi r square. That's why 4 pi r square here. Now, why 4 pi r square in the denominator? Because if the second charge is at a smaller distance, the size of sphere is less. The smaller distance means the radius is less, you get smaller sphere. But electric force will be more, because the distance between the charges is less, you get more electric force. If the charge is farther from this charge, bigger radius means bigger sphere. Bigger sphere means bigger 4 pi r square. But bigger 4 pi r square means you are farther, radius is more, so you are farther, weaker electric force. So, this 4 pi r square and this force are inversely related. That's the reason F equal to Q1 Q2 by 4 pi r square, because they are inversely related. Now, here instead of 4 pi r square, you have 2 pi d. There, what is r? R is the distance between the two charges. Or if you take a sphere, then the distance is nothing but radial distance, radius, r I have taken. Similar to r, here you have d. What is r there? R is the distance between the charges, spacing between charges. Here d is the spacing between the electric conductors, in which electric current is flowing. D is the spacing between the electric conductors. Obviously, if they are farther, weak magnetic force; if they are closer, strong magnetic force. It's simple common sense, intuitive. Now, there you have 4 pi r square, here you have 2 pi d. Or if you want to make a one-to-one analogy, there you have taken r as the variable to indicate the spacing between charges. Here also you take r as the spacing between the conductors. Then I should rather write it as 2 pi r. Just assume instead of 2 pi d, 2 pi r. Just the name of the variable is changing, nothing else. Instead of 2 pi d, I am writing 2 pi r. So why 4 pi r square here? Why 2 pi r here? Because you take a conductor, current is flowing in this conductor. Current carrying conductor is surrounded by magnetic field. How the magnetic field is surrounding? Like this. Current is flowing like this. It is surrounded by magnetic field, circulating manner. Current is here, magnetic field is surrounding this. What is this? Geometrical, it's a circle. Earlier for electrostatics we have seen, in Coulombic force we have seen, we have taken the analogy of sphere. But what is this? It's a circle. Now, if this is a conductor, you are standing at this point and measuring the magnetic field or experiencing the magnetic force. Then this is a distance. If you are here and measuring the magnetic strength of magnetic field or experiencing the magnetic force, this is the distance. You get a bigger circle. But what is the circumference of the circle? That means whether you are here or whether you are here or whether you are here, you measure the same magnetic force, isn't it? So what is the circumference of the circle? Circle will have circumference. Sphere will have surface area, 4 pi r square. Circle will have circumference, which is 2 pi r. If you are nearer, smaller 2 pi r. If you are farther, bigger 2 pi r. Bigger 2 pi r means you are farther, so you have weak magnetic field. Smaller 2 pi r means you are nearer, you get strong magnetic field and strong magnetic force. That's why they are inversely related. Just I have explained in terms of replacing d with r, that's all, 2 pi r. So this is the entire thorough understanding of Ampere's force law, which deals with the magnetic forces existing between electric conductors. Now coming back, force is a vector, whether it is electric force or magnetic force, it's a vector. Now however the direction of these forces. Now in electrostatics we have like charges will repel each other. Like charges means charges having the same polarity. Like charges, whether it is plus plus or minus minus, like charges will repel. Like charges will repel each other. Whereas here like currents will attract each other. Like currents means currents in the same direction, going up in both conductors or coming down in both the conductors, I1, I2 in the same direction. Here like charges will repel, here like charges will attract. Here unlike charges, plus minus or minus plus, which are Q1, Q2. Here unlike charges will attract each other. Here unlike currents will repel each other. Why? What is the reason? The reason is simple. There you have like unlike charges. So here when you take positive positive, two charges, they repel. But when you take here positive negative, they attract. In the case of magnetostatics, magnetic fields, you take I1 and I2 in the same direction. Now what is the direction of magnetic field? It gives right hand thumb rule, gives the direction of magnetic force. Current is going up, so magnetic field is like this. In another, like this. At this point, the force is towards me. In the other conductor, it is going also up, like currents. What will happen here? Right hand thumb rule, like this. So at this point, what is the direction of magnetic field? It is given by current is going up, like this. Direction of magnetic field. Here also, the current is going up. What is the direction of magnetic field? Like this. See, this is opposite to this. So what will happen? It's like this is the north pole for this magnet. This is the north pole for this magnet. That is opposite direction. But now If I say this is north south, this is north south, so what will happen when you take like currents? There like currents repel. Like charges will repel. Here like currents, what is happening? They attract, because this is in one direction, this is in other direction. If I say this is north pole, then opposite to this it should be south pole. If I say this as south pole, opposite to this should be taken as north pole. And you know, north south will attract, north north will repel. Even though the current is in the same direction, magnetic field is also given as per right hand thumb rule, but at this point they are in opposite directions, which makes attraction. That's the reason in electrostatics we have like charges which repel, here like currents attract each other. That's the difference. Unlike charges attract each other, unlike currents here repel each other. That's the difference that you have to keep in. So this is all about thorough understanding about the Ampere's force law, which deals with magnetic forces between electric conductors.